Welcome to the 945th monthly meeting of the Amateur Telescope Makers of Boston. Rich Nugent couldn't be here tonight. He had a family emergency, so as vice president, I'll step in his place and run the meeting tonight. Our guest speaker will be Dr. Mahboubeh Asgari-Targhi from the Harvard-Smithsonian Center of Astrophysics, and her talk will be Here Comes the Sun. So it looks like this is a comment from Julie. Flat Earth Space Program. 3, 2, 1, slip off. We have slip off. 32 minutes past the hour. It's a good one. We've got the observing committee report and a quote of astronomy to the selfish becomes astrology by Ralph Waldo Emerson. So the upcoming sky events, looks like October 14th to November 11th. On Saturday, October 16th, Venus will be 1.5 degrees north of Antares, low in the southeast after sunset. Thursday, October 21st, Orionid meteor shower peaks, expecting around 10 to 20 meteors per hour. Thursday, October 21st, Uranus 2 degrees north of the moon, low in the east at sunset. That could be a treat to hunt down, easier to find. Uranus can be pretty small, especially if you're in a Dob. So having a nice reference like the moon nearby is good. And Monday, October 25th, Mercury reaches greatest elongation west 18 degrees in the morning. Tuesday, October 26th, moon is 1 degree north of M35. Look northeast at moonrise at 8:50 p.m. So at 1 degree separation, if you have a nice wide field refractor with a wide eyepiece, you might be able to get both in there. That could be pretty cool. Although, we'll see if the moon washes out. It'll be a challenge. Could be fun though. So, and on Friday, October 29th, Venus reaches greatest elongation to the east at 47 degrees. And late October, early November, the Torrid meteor showers should be visible. In this one, fireballs are common, which are always a treat to see. Although I always end up looking at the wrong, either looking down at a piece of paper or an eyepiece and hear everyone else go, oh, there it was. So whenever you can, take a chance and just stare up at the sky for a while. Hopefully you'll get rewarded. And Thursday, November 4th, Uranus reaches its opposition at magnitude 5.6. Saturday, November 7th, daylight saving times ends at 2 a.m. So I only get another hour. Monday, November 8th, Venus is 4.5 degrees east of the moon at sunset. Look toward the southwest. And again, that should be a nice pairing. Venus near the horizon is always really beautiful. Wednesday, November 10th, Saturn is 6 degrees northwest of the moon at sunset. Thursday, November 11th, Jupiter is 4 degrees north of the moon at sunset. So you got a couple days in a row where you get to see the planetary motion in motion and just kind of see our place in the solar system. Always nice to track. So the Observer's Challenge object for October 2021 is NGC 6857, an emission nebula in Cygnus. Cygnus is absolutely chock full of tons of beautiful emission nebula and dark nebula. So this one should be a real treat. I'm not sure if Glenn is here, if you'd like to talk about it or not.
Which I didn't see him in the member list today.
So it looks like it should be hopefully has some fairly good guide stars nearby for star hopping. So you've got kind of the main cross of Cygnus. And then it looks to be about halfway between the central star and Albireo. So if you kind of start halfway between those and go southeast of New Cygni, you'd probably be in pretty good shape. Although being an emission nebula, it might not jump out at you in the finder scope. So having this tighter field star map, I think Glenn usually pulls these from the AVSO website. So with a tighter field map like this, you can probably hone in. I'm assuming that's New Cygni there. Not sure. But once you get close, you can star hop your way there and confirm that you're pointing at the right spot, and then switch to a higher power. And since it's an emission nebula, a nebula filter could help. This one is hydrogen alpha, but a UHC filter could do it too. So this is a photo from Doug Paul. He uses a Canon RA DSLR, or no, is it mirrorless? But uses an enormous telephoto lens on an equatorial with an extender. He's got really nice color rendition in the stars. You can see the emission nebula there. And then I think this was a sketch from Glenn, where you can see a lot of the same stars. So the very bright star next to the nebula is able to pick out. So that would be a good one to hone in on this star with your finder scope, if you can pull it out in the finder scope. But to hone in on this star before you switch to the ultra high contrast, and just make sure that you've got this star close to center of field. Then you can try swapping the filter in and out and see if you can detect anything. And this photo is from Mario Mata's enormous 32-inch telescope. Looks like a mostly hydrogen alpha picture, and just the incredible depth that you can pull out with that. It looks like the nebula there is just on a background of hydrogen alpha. And the whole region of Cygnus, there's tons and tons of massive sprawling emission nebula. It's fantastic in wide field photography. Or I got to use night vision monocular with the hydrogen alpha filter with like 1x magnification and looking up at the Cygnus region. It's just incredible how sprawling the massive hydrogen alpha region is. It's really incredible. So I guess we'll move on to the talk. So tonight's speaker is Dr. Mahboubeh Asgari-Targhi from Smithsonian or Harvard Smithsonian Center for Astrophysics. Dr. Asgari-Targhi received her Bachelor of Science degree in Theoretical Physics from University College London in 2002, her Master of Science degree in Quantum Fields and Fundamental Forces from Imperial College London in 2003, and a PhD degree in Applications of Mathematics to Solar Physics from University College London in 2009. She's currently an astrophysicist working at the Harvard Smithsonian Center for Astrophysics in Cambridge. And her primary research areas include solar physics, plasma astrophysics, with a particular emphasis on solar corona and solar wind, as well as applications of topology and geometry in astrophysics. So I'm not sure if she is in the meeting yet.
I am, yes.
Oh,
hi.
Fantastic. Hello. How's it going?
Good, thank you.
So glad you could come to talk with us.
Sure,
I'm looking
thank
forward
you.
to it. Sounds like a great talk.
Thank you.
Do you have host permissions? I'm just trying to find.
Should I share my screen?
Yeah, she's all good.
You can
So
take it away. Okay.
yeah,
Let's-
Corey, go ahead and stop sharing and
you.
she can take over.
There we go.
Thank you. Okay. Thank you for your time this evening. I am going to talk about the sun, its structures, and some of the phenomena that happens on the sun. And in the second part of my talk, I'll talk about my research, which is on modeling of solar wind and coronal heating. The sun is a yellow dwarf star where magnetic forces dominate over gas pressure and gravity. If we compare some of the structures of the sun with the Earth, for example, the radius of the sun is about 700,000 kilometers. It's 109 times the Earth's radius. The density of the sun is about a fourth of Earth's density. It's 1,400 kilogram per meter cube. In terms of the mass, the sun has a mass that is about 6 orders of magnitude larger than the mass of the Earth. And the rotation of the sun, what is interesting about the sun is the pole and the equator rotate at different rates. So you have the equator rotates or revolves every 25 days, and the poles rotate about every 33 days. And this difference in rotation between equator and the poles create what is known as differential rotation. And that can result in the creation of active regions and sunspots on the sun. The sun consists of electrically charged gas known as plasma. The core of the sun is mostly hydrogen, as it's shown in this figure. At the center, you have nuclear fusion taking place, where the temperature is about 15 to 20 million Kelvin. And then you have different structures. For example, you have, as you move away from the core, the temperature drops. In the photosphere, you have a few thousand Kelvin. That is the temperature of the photosphere. And then when you move further away between photosphere and the corona, the temperature suddenly increases. Some of the features that are shown here, for example, prominences, chromosphere, sunspots, and solar wind are the topics that I will cover in the upcoming slides. Here, I'm going to show you a movie where you can see the photosphere at, at 6,000 degrees Kelvin, and then you can see how the temperature changes. So here is the movie. You can observe the chromosphere at 60,000 degrees, and then this is the corona, 1 million degrees Kelvin. Again, corona at 1.5, and last one is the corona observed in X-ray. So let me play the movie again. So you see the variation of temperature that corresponds to the observations of photosphere, chromosphere, and corona in different wavelengths. The photosphere is characterized by magnetic fields. So basically what you see, the image that you see on the right is from a magnetogram known as HMI, and it's an instrument on Solar Dynamics Observatory. Solar Dynamics Observatory is a space instrument. And these black and white dots that you see are sunspots. And if the magnetic field is towards the sun, then you have those black dots. And if the magnetic field is away from the sun, you have those white dots. The sunspots are where the active regions that are where the sun has its most magnetic activity originates from. And for example, in this image, based on this magnetic map, you see there are at least 2 sunspots here. The chromosphere is also identified as a region where magnetic activity are a lot and are very important. And the magnetic field lines also play an important role in the heating of the chromosphere, as well as the active regions on the corona. In this image, you observe the photosphere, for example, at 4,500 angstrom, you see the sunspots. Then you see the chromosphere, the red image where it's in helium-2, 3 or 4 angstrom, and that is the wavelength that is mostly showing the chromosphere at, and it's basically at a temperature of tens of kelvins, tens of thousands of kelvins, about 50, 60,000 Kelvin. And the second row shows the corona, where you have the corona is observed in 171 angstrom, 193 and 94 angstrom. And each of these wavelengths correspond to different temperatures in the corona. The corona has temperatures of 1, 2, 3 to 4 million Kelvin. The core of the corona, the core of the active region, is hotter than obviously the coronal loops. So the core can get as hot as about 7 or 8 million Kelvin. The best way to observe the sun's corona is during the eclipse. And the corona was identified to have a temperature of a few million degrees by Eldon in 1942. It has a thickness of about 690,000 kilometer to 1.5 million kilometer. The structure of the corona is that because of the high temperature, you have ionized gas that is known as plasma. So you have ions and electrons in the corona. It also, what is interesting about the corona is that it, despite this very high temperature, it has a very low density compared to photosphere and chromosphere. So it has a density of about 10 to the 9 particles per centimeter cube. Another very interesting feature of the corona is it has a low pressure. The pressure in the corona is about 0.1 to 0.6 pascals compared to the pressure that we see at the sea level on Earth, that is about 100 kilopascals. So approximately the pressure on the Earth is about 1 million times higher than the sun's corona. So this variation of temperature between photosphere and the corona, which you, as we move away from the photosphere going towards the chromosphere and the outer layer, the corona, based on the laws of thermodynamics, you expect that the temperature should drop, but this isn't what happens. So you see the increase in the temperature. For example, in this plot, you see the y-axis is the log of temperature, and the x-axis is showing the height above the limb in megameter. So as you move from the photosphere to the chromosphere and to the corona, you see there is this increase in the temperature. And you have a temperature of a few thousand Kelvin, then tens of thousands of Kelvin in the chromosphere, and in the corona is a few million Kelvin. And you see, if you look at a plot for the density, the dashed line, you see the density is in the photosphere, about 10 to the 16 particles per centimeter cube. And you see suddenly you have that change in the density that in the corona is reduced by 6 or 7 orders of magnitude. It's about 10 to the 9 particles per centimeter cube. This gives rise to this complex problem known as coronal heating problem in solar physics. The basic structure of the solar corona are the coronal loops. They connect regions of opposite polarities. And if one wants to understand the corona and its heating and its magnetic structure, the best way to develop that understanding is using the coronal loops, because they more or less follow exactly the same features that exist on the corona. They have the variation in the density exists within a coronal loop. If you start from the photosphere and go towards the corona, the variation in the temperature is also observed in the within the coronal loops as well. So in this part of the talk, I will carry on discussing different structures on the sun, and then later on in the last part of the talk, I will talk about the modeling of the coronal heating. Here we are going to look at solar cycle. So every 11 years, the sun's magnetic field is flipped, and you see the variation in the magnetic activity on the sun. For example, this is cycle 23, where if you look at from 1996 to 2006, You see between 1996 and 1997, sun is not very active. From 1998 to 2004, you see there are those bright features. These bright regions correspond to sunspots, and these are the sunspots are where the active regions originate from. So these are the bright features that you see are where the sun is very active. And again, between 2004 and 2006, there is a reduction in the sun's activity. This plot shows the daily number of sunspots from 1940 to 2020. You have on the y-axis sunspot numbers, and here is the year that covers how much the number of sunspots varied between 1940 and 2020. And in the last couple of decades, the sun's activity has been reduced. One very interesting feature of the sun is the solar prominences. The solar prominences are regions that are cooler than the corona, and they have less density compared to the corona. So let me play this movie where we can see the prominences. So in solar prominences, when there is the acceleration and ejection of particles that take place. And what is interesting about them, if I play this movie, the materials is basically ejected to larger heights. The magnetic field strength in solar prominences is not as strong as it is in coronal loops. And the solar prominences are also behind the coronal mass ejections. So the coronal mass ejections sometimes are the result of solar prominences. Another very interesting characteristic of the sun is solar flares, where you have these very impulsive, intense, energetic events that take place. And the solar flares happen when the coronal loops interact with each other, and they create what is known as magnetic reconnection. They have an energy of 10 to 22 to 10 to 25 joules, depending on what types of solar flare they are. If there is an X flare, as I'm going to show in this movie, then it has the highest energy. So here we can see this is when an X flare takes place, and an enormous amount of energy is released as a result of solar flare. Coronal mass ejections are also very large events that eject enormous amount of matter and energy from the sun. They have an energy that is comparable to flare energies, about 10 to the 25 joules, and they have a mass of about 10 to the 13 kilogram. I'm going to show you this movie that is from LASCO, where basically you almost create something like an eclipse, cover the surface of the sun so you can observe the coronal mass ejections much better. So here is a coronal mass ejection taking place. And again, you see there are lots of particles that are ejected, and these particles could travel towards the Earth and disturb the Earth's magnetic field. That usually result in auroras. So move to the next one. The next very important feature of the sun is solar wind. Solar winds are, there are two types of winds associated with the sun. One is a slow wind and the other one is a fast wind. And solar wind, basically, if they originate from the equator, near the equator, and they have a speed of about 400 to 450 kilometers per second, they would be considered as a slow wind. If they originate at the pole of the sun, then they usually have a speed of about 600 or above 600 kilometers per second, and they are considered to be fast wind. They both types of wind originate from open field, but the open field are positioned, if it's at equator, it's a slow wind. If the open field is at the pole, then that would be the fast wind. Again, in the case of solar wind, you also have ions and electrons that are streamed out of the open field and travel along the open field. And if they reach the Earth and get through the Earth's magnetic field, they create auroras, or they disturb the Earth's magnetic field. To understand the origin and structure of the solar wind for both fast and slow wind, what we do is we use the magnetic modeling using the magnetic map that I showed earlier on, and they measure the magnetic field and they fit magnetic field lines to the regions that we suspect the wind could originate from. And this is usually known as the potential field modeling, where you can fit a field line to an open region on the sun. The next part of the talk, I'm going to talk about the coronal heating. There are many coronal heating theories that have been proposed, but there are two that are the most important ones. One is the magnetic reconnection, and the other one is the wave heating. The idea of the magnetic reconnection is if you have a series of coronal loops and the magnetic field lines become stressed such that the field lines cannot tolerate any more pressure or stress, then the field lines reconnect and they release their energy. This release of energy is known as nanoflare, and the idea was put forward by Eugene Parker in the 1980s. In the case of the wave heating mechanism, you have the waves that are generated at the photosphere. These waves travel towards the corona, they create turbulence, and that turbulence could result in heating the corona and creating the high temperatures of a few million degrees in the corona. What is important about both of these theories is that photosphere plays a very important role. So you have, if you're talking about coronal loops, they originate from the photosphere, they begin and they end at the photosphere. So, and you have oscillations, you have what is known as granules and supergranules at the photosphere. And the oscillation at the photosphere, either in the case of wave heatings, generates the waves that create turbulence in the corona, or in the case of nanoflare heating models, stresses the field line where this stress is transported to the corona and then released in the form of nanoflare as a result of magnetic reconnection. In the case of stress magnetic field lines, if you are looking at the magnetic field lines that are stressed, for example, imagine these two planes where you have these strings, and if I apply motions at these two planes, then you will end up having a stress field lines. And if I line tie the end of the field lines, then you have the middle image that is quite similar to what you get on the right, that is the coronal loops. So once these motions at the photosphere are applied to the end of the field line, and if these motions transmitted to the coronal part of the loop, then you have a stress created in the coronal part of the loop. And once that stress gets too large, then the energy is released in the form of flare or nanoflare. In the case of coronal heating, you need only small flares to be able to heat the corona to temperatures of a few million Kelvin. How does the reconnection takes place? When you stress the field line at the photosphere, your magnetic field lines are misaligned. And if they are misaligned in a way that you have an angle of 30 degrees created between these two field lines, then the angle of 30 degrees is enough to result in magnetic reconnection, and releasing the energy into a nanoflare. This is an image from a rocket known as HI-C. For example, there are people who have worked on HI-C images and looked at these regions where they assume there are magnetic field lines that are braided, and then they measure the magnetic field, and there is correlation between the magnetic field strengths and the stresses that are built up within the field line and the energy that is released. So they can, based on the topological structure of the magnetic field line, they can measure the temperature, and this is a mechanism that the stress field lines release their energy and create a temperature of a few million degrees Kelvin. The model that I have been working on is the wave turbulence, and the idea of the wave heating was put forward by Avery Schatzman in 1949, where the waves carry the energy from the photosphere through the chromosphere to the corona. And what is fascinating about the sun is because sun is made up of plasma, therefore it basically supports several types of waves. For example, the most important types of waves that exist on the sun are magnetoacoustic waves and alpha waves. The magnetoacoustic waves are the sound waves that have been modified because of the presence of the magnetic field. And the alpha waves are the low frequency waves that basically you have the plasma traveling in the direction of the magnetic field. And because they have low frequency and because they are they travel along the magnetic field line, they can carry energy along long distances. So they can carry heat and energy from the photosphere towards the corona. In the modeling that I have worked on, with my collaborators, what we have done is we have considered one single flux tube. For example, as you see in the cartoon here, you have the two planes are where the photosphere is. So we apply motions at the photosphere. And as a result of these foot point motions, we generate alpha waves. And the alpha waves travel upward from both sides along the loop. And because of that variation in the density that I showed earlier on, you will have reflection of the waves at the chromosphere. And some of the waves get through the corona from both sides. Waves are coming and they meet in the corona, they crash into each other, and that is what results in the heating of the corona. What is interesting is because of the variation of density between the transition region and the corona, you also have some waves being reflected back at the transition region. And as a result of the interactions between incoming and outgoing waves in the transition region, you have chromospheric turbulence that could also increase the temperature of the chromosphere. So with the wave turbulence, with the alpha wave turbulence, you have a way of explaining both the heating in the chromosphere and in the corona, and therefore you can account for the temperatures of tens of thousands of Kelvin in the chromosphere and millions of Kelvin in the corona. The way we generate the waves are, we look at two equations. The two main equations that we use are the momentum equation, where you look at the variation of velocity with time, and magnetic induction equation, where you're looking at the variation of the magnetic field with time. So what we do is, for example, in one of the studies that I did with my colleagues, we looked at an active region on the sun from May 5th, 2010. The region is this region, and you can see we have a few coronal loops. And what we did was, using the magnetogram in this image, we fitted magnetic field lines to the active regions. So here you can see we fitted about 10 field lines to this region. And what we did was, this is the known as nonlinear force-free field modeling, where you measure the magnetic field line of the coronal loop that you fit with a curve. the information that you get is you get magnetic field strength at every point along that field line. You get the height at every point along that field line. You get the position at every point along the field line. And then what you do based on those two equations, you introduce foot point motions at the foot point of the field line. Suppose we are looking at field line number 6, and then you generate the waves and create turbulence. And then you look at temperature density that comes out of turbulence and see if it is consistent with what you get for the temperature and density or other parameters such as magnetic field at the corona. Here I'm going to play a movie that is, sorry, I need to. So the movie is this. This is one of the movies is the result of the simulations that I have done with my colleagues. What you see here is you see that the foot point motions are the two ends of the panel. So the first panel is ZY, where if I stretch that coronal loop that I showed, say number 6, and I look at it from sideways, and as I'm generating the turbulence, I create a movie. So that's what we did. So you're looking at the sideways, ZY, ZX, and then the cross section of that field line. So what you have photospheric foot point motions result in the generation of the waves. Then the waves travel upward. Here are the transition regions. You have the two transition regions, TR1 and TR2 here. So the waves travel upward, they're reflected back.
Exited
Pardon?
I think you exited full screen. The mouse is going off the presented screen.
Oh, sorry,
are you playing a movie outside of PowerPoint?
Yes, yeah.
You'll need to reshare the screens with that with that movie.
You share. Okay, sure.
I see it.
Well, can you see it now?
Yep.
Okay. Sure. Okay, so you can see that at the foot points, at the photosphere, the waves are generated. Then they travel upward, move towards the transition region. They're coming from both sides. And then some are reflected back and some move through to the corona. When they meet in the corona, you see all of those light blobs are when the waves crash into each other. And those are the regions where you have higher heating and higher temperature. So if I play the movie again, you're looking at ZY and ZX. So they're looking at the loop sideways. And then the bottom panel is showing the distortion of the cross section of the flux tube as a result, or coronal loop as a result of the waves that are generated. So what we found, in the next slide, I'm going to show you, if I just go back. Maybe. So when we did model the turbulence, alpha and wave turbulence in the coronal loops, what we found as a result of that modeling is a series of measurements for temperature, density, the radius of the magnetic flux tube, and the alpha speed. For the temperature, you see that the temperature at the chromosphere is about 10 to the 4 Kelvin. And then it increases, and in the corona, you have a temperature of about 1.5 to 2 million Kelvin. So the temperature is consistent to what is seen from the observations. The same goes for density. So you have that variation in the density that I was talking about. At the photosphere, here you have a density of 10 to the minus 7 gram per centimeter cube, and in the corona you have about 10 to the minus 14. So the density is also consistent to what we have in the observations. And then we expect, because you have the variation of the magnetic field between the photosphere, chromosphere, and corona, you expect the radius of the coronal loop to also change. So you also see the variation in the radius in panel E, and in panel F, you see the change in the alpha and speed. What is interesting is because you're going from photosphere, a very dense environment, to corona, a less dense environment, the alpha and speed increases drastically, and you can see that you start from 10 kilometers per second in the photosphere, and in the corona, the waves have a speed of about a few thousand kilometers per second. So with the alpha and wave turbulence, you can explain the heating of coronal loops having temperatures of 1 to 3 million Kelvin. And in summary, what I did, I hope that I managed to describe some of the characteristics of the sun and also the heating theories that have been put forward for modeling and characterizing the coronal heating and chromospheric heating. And the fact that if you are looking at loops that are as hot as 2 to 3 million Kelvin, you can explain them by the alpha and wave turbulence. And the same mechanism can also explain the heating of the chromosphere. And if you're talking about structures or loops that are hotter than 3 million Kelvin, then we need a mechanism, either nanoflare heating or other types of magnetic reconnection. And that's the end of my talk.
That's fascinating. So many mysteries I never knew even existed. I always see the pictures of the beautiful flares. I know about the magnetics, but I didn't know about the heating paradox.
Sure.
It's all new to me.
Good.
Very cool.
Thank you.
I have a question.
Sure.
Those 4 graphs showing the motion in the loop indicate about 250, 300 seconds transit time from one end to the other.
Yes.
Including the photospheres at each end.
Yes.
So how far apart are those 2 photosphere junctions or endpoints?
Okay, it depends on how big your coronal loop is. So if you're talking about a loop that is, say, 100 megameter or 100,000 kilometer, then usually the foot points is about, the distance between 2 foot points is about maybe tens of thousands of kilometers. If you're talking about a coronal loop that is very high and very large and very long, then the foot points are usually further away from each other. So it depends.
Thank you.
Sure.
I have a question.
Sure.
The Parker space probe, the Parker probe, even though it's been out relatively short period of time, any surprises in data that it has collected?
The Parker Solar Probe, yes, it has. So one of the things that it has found is that one of the main results that came from Parker Solar Probe was the reversal of the magnetic field. So that the magnetic field away from the sun, large distances away from the sun, flips and changes direction. In terms of the work that I do, I have started comparing some of the modeling of solar wind, the fast and slow wind, with Parker probe observations, because they get very good observations of the magnetic field and density fluctuations. And that's what I have started looking at, comparing modeling results with the observations.
Thank you.
Sure.
Kai, do you have a question? I see you have your hand raised.
Yes, I have a question about, is the coronal loop and prominence the same thing, or? what's the relationship between the two?
Sure. No, they are not the same thing. What is for a coronal loop, the magnetic field is very strong. So the plasma, the structure of the coronal loop, the plasma follows the magnetic field strength. And the magnetic field strength is a lot larger than it's in a prominence. So you see the reason that you have all of those ejections of particles and mass into the environment around a prominence is because the magnetic field strength doesn't have a very strong hold on the plasma. And another characteristic of a prominence is the lower temperature. So it has lower temperature. The temperature is similar to the temperature that you have on chromosphere, maybe about 50 to 60,000 Kelvin. Whereas in a coronal loop, you have a larger magnetic field. Its structure remains intact. It is the plasma is bound by the strength of the magnetic field, and the temperature is also higher.
Thank you.
Sure.
There's
Hi,
a
Corey.
question in the chat. Yeah.
What was that,
Or
Tom?
there's a question from Bernie's iPad Air 2. And the question is, he is wondering what the latest forecast for the solar cycle is.
I think my understanding is based on some of the, we usually have a space weather report every week. And in the past few weeks, it looks like that sun is becoming more active. So we have looked at the active regions and the number of sunspots. And it seems to be increasing. The sun's activity seems to be increasing.
But everyone with the solar scope will be happy.
Sure.
In the pictures of the magnetic field across the surface of the sun, what kind of instrument is used for that? Is it something that's directly measured or inferred?
Which picture?
I think it was the third slide from the end,
Oh, third slide. Yeah, sure.
or 29.
Oh, this one? This one?
One up. The next
This-
picture up. So the
this one.
upper left picture, the grayscale with the black and white showing the magnetic.
This one?
On slide 29,
Oh, slide 29, sure. Oh, this one?
and then the first picture in the upper left.
Oh, the upper left is NDI is a magnetometer on a space instrument. So every right now the magnetometer's data that I use is HMI, that is on Solar Dynamics Observatory. Every one that I have used are a space instrument. I have just started looking at using the magnetic maps from a ground telescope. I haven't used it in the past. So, yeah. I mean, almost every single observation that I showed are space observations.
ST atmosphere gets in the way.
Exactly, yes.
Scatters
yes.
everything.
Sure. Usually they have better resolution and they're, in terms of the magnetic field measurements, so some of them are much more reliable. But there are also, right now is the DKIS observatory that they are going to have a high resolution magnetic imager. That the idea would be hopefully to use ground telescopes as well.
Hi, I have a question, Mark.
Sure.
You had mentioned something about that the poles rotate at different speeds than the center of the sun. So it's almost like it's a sloshing where the center is going faster or slower. It would be faster, right?
The center is going, bring my notes. So the center, the equator is going slower. It's 25 days. And
Okay.
the poles, yes.
So in terms of when did we discover that? I know that I've been reading a lot about how that affects where the solar flares kind of form, and then they go down and they follow basically the day line, essentially, I guess, where one is spinning faster than the other, and they seem to follow the two places where those meet.
Sure.
And I would think that would also, that kind of gravitational dynamic would be what's creating a lot of these prominences and flares. And if that's the case, does that rotation, and this might seem like a stupid question, but does that rotation speed ever change? And is that why there's cycles? Because it would seem to me like if that's always happening, then you would always have the same dynamics going on, and the flares and I mean, the sunspots would be showing up, but maybe it just happens so slowly in our timeline that we see it as a cycle.
That's a good question, and I don't have a good answer for it. I don't think the fact that you have, my understanding of the difference in the rotation rates between equator and poles, and I always mix the two, which one is faster, which one is slower. That's why I wanted to look at the slide, is that the rate, because they rotate at different rates, is what creates this differential rotation is what results in some of the people who work on solar dynamo. They model that then you will have the magnetic field lines that are already, there are theories that believe that the magnetic field lines do not form at the photosphere, unlike what we, for simplification and the way we model, we cannot go below photosphere because we don't see anything. So there are people who work on solar dynamo and they believe that no, the magnetic field originates way below photosphere. And the reason is this difference in the rotation of the sun at the poles and at the equator already results in the change of the internal structure, and the magnetic field has already been formed way below photosphere, and then they suddenly appear on the sun. Whether it's related, the existence of sunspots or flares are related to this differential rotation, I don't know. I don't have an answer for it.
I don't know. I find that fascinating because it's like you have it would be like if you had a tennis ball and part of the tennis ball is spinning at a faster rate than the middle is spinning, and the dynamics must be incredibly bizarre.
Yes,
just to see what would be going on with that.
Exactly.
Oh, and the other, really quickly, because the corona sphere, which is what we see in the eclipse, right?
Yes.
How far out does that go? Do we know what the furthest reach out? I mean, it's obviously not always in the same place, but it's roughly in the same place. Do we know how far out that goes?
I think so. If you're talking about one of the ways to that I said in the slides to model the corona is look at the coronal loops. So how high a coronal loop can get. A coronal loop can get maybe a few thousand kilometers high, right? So if you have a loop that is very long, say 300 or 400 megameters. I have modeled coronal loops that are as long as that. So the height goes maybe about 10,000, 20,000 kilometers. So that would still be considered corona, right? But if you're looking at so in other words, I don't have a good definition for where the corona ends and where, for example, other things start, right? But for the coronal loops, I can tell you that as high as the tallest loop that you can see gets, then that would be what you consider to be a coronal loop. If you can fit it with a magnetic field line, and it's maybe tens of thousands of kilometers.
Okay, thank you.
Sure.
It's like Eileen has a question of do solar spicules have an effect on the corona's temperature?
That's a very good question. Yes, so the specules are considered to be the structures that transfer energy. So there are people who model specules using alpha wave turbulence, and they believe that the way you transmit energy at the chromosphere to the corona is through the specules. So there are people who work on that. Yeah. So they definitely play a role in the way the chromosphere is heated.
The differential rotation, is it likely that most other stars behave in that way, or is there a way that we could verify it on other stars?
I think definitely there are so many fascinating facts about the sun that can definitely be I don't think we can say it's only the sun that behaves this way, but part of the reason that we know the sun so well is because we do most of the observations, instruments that are sent to space only observe the sun. So there are, for example, I do know that I have colleagues who work on modeling of solar type stars, and so many of the structures that you see on the sun can be, they do believe that they also happen on other stars. And those are based on some of it is based on ground observations. And I don't know if, I don't think there are space observations of other stars, but I do know that there are people who do the comparison between the sun and other stars using the ground telescopes.
Very cool. Any other questions?
Alva posted one.
Okay, so we have Alva's asking, how did you get the pictures of different temperature regions? Is there a relationship between radiation wavelength and temperature? Is it
Yes,
black body?
exactly. Yes. So the spectroscopy is used to get the temperature for different regions, and the different wavelengths are associated with different temperatures. So if you are showing an image of the sun, like the one that is currently shown on the slide number 2, this is 171 angstrom, and that is associated with a temperature of 1 million Kelvin. And that is ion 9. So when it's an ion that has lost 9 electrons. If you're talking about ion 94 angstrom is ion 17 or 18. So that is usually associated with a few million degrees Kelvin. So there is a correlation. There is a connection between the wavelengths and the temperature.
Okay. So it's an actual like energy state. It's not just
Exactly.
a band of black body.
Exactly. Yes. Yes.
Very cool.
All right, I have one other question, and it's another one of my far-reaching. I'm curious, all the planets have an escape velocity, and you see the loop going up, and then you see like a coronal mass ejection where it's actually able to go beyond the gravitational pull of the sun. So do we know roughly what the speed, and it must be pretty fast, that particles or whatever have to be going to not be pulled back into the sun?
I think that would be about hundreds of kilometers per second. It would be similar to speed of the wind, about
Okay.
500 to 700 kilometers per second. But also it's when the magnetic field is when they escape the magnetic pull of the sun, if you like, within a coronal loop. That's when, for example, when you have magnetic reconnection is when two magnetic field lines are close, they touch, and then they're misaligned by an angle, and then there is reconnection. And at the point of reconnection, then the magnetic field loses its grip over the particles, and the energy is released, and the particles move away, right? So that usually is a few hundred kilometers per second.
Okay, so if I have my physics right, that the magnetic field is much more powerful than gravity, because gravity is pretty weak.
Exactly. So on the sun, especially within a coronal loop or even in solar wind, the magnetic field definitely plays a very important role. So it's important, more
Okay.
important than gravity.
Thank you.
Sure.
Thank you for a good talk.
Of course. Thank you.
Eileen is asking, can a coronal loop be seen visually with a telescope during a total solar eclipse?
Actually, you know, one of these, there was this image of the sun's corona. This is an image of the sun during an eclipse. So you do see, obviously, you won't be able to see the coronal loops that are near the disk center, but you can see those that are on the periphery of the sun. So if it is away from the disk center, if you have an active region that is away from the disk center, then you can observe it during a solar eclipse. But if it's close to the center of the sun, then it's obscured by the moon.
I have a question. What software do you use to perform the simulations that you're doing? Is that written at the Center for Astrophysics, or is that commercial software?
No, this is the software that we use to solve the equations for momentum and magnetic induction. It's a Fortran program. And then, so the equations are solved using the Fortran. Then to do the modeling of the magnetic field line, we use IDL software. And then to create the movies, then we use IDL. So we read back the data files from Fortran into an IDL, and then we create image files. And from those image files, we make a movie.
So you guys are writing the Fortran?
Yes.
Difficult.
Yes.
Thank you.
Sure.
So John Harrington is asking, is there any chance to observe, or at least infer the location of alpha waves from the ground by using spectroscopy, looking for Zeeman effect splitting?
There is, but you know, the way to validate part of the one thing that I didn't include the talk because of the time was, so it's all well enough to model and say, okay, I create the temperatures and here it is, and there is alpha waves on the sun. But how do you know that? What is the observational evidence for alpha waves? So one way is if you have an instrument on the ground that observes the sun and can characterize the alpha waves. The way to do that is alpha waves have a velocity that their velocity is basically they oscillate perpendicular to the magnetic field line. So you have a velocity that is known as non-thermal velocity. So there are space instruments that have a map. There is a Doppler velocities, and then from the Doppler velocity, you can deduce the non-thermal velocity. And then you say, I have the non-thermal velocity within a coronal loop, and then I use that, I see it from the observation, and therefore there are alpha waves that travel within a coronal loop and create a temperature. I have used the space observations for these non-thermal velocities, but I have not used ground observations. Again, with DKIST, people are hopeful that we will be able to use non-thermal velocity measurements from the ground and compare it with the non-thermal velocity you get from modelings.
Very cool.
Sure.
If there are no more questions, we might officially end the meeting. Usually we hang around and just.
I have another follow-up question. So, is this a observation of alpha wave, or is there any other like a critical observation could distinguish your wave heating model with, like, say, the mechanism of using magnetic reconnection to explain coronal heating? So, like, is there like a critical observation that could distinguish between the two models?
Yes, that's a very good question. Yes, there is. So in the magnetic reconnection, you expect, because you have this instant release of energy within a coronal loop, therefore the speed that they need at the point of reconnection, the speed of the alpha waves, because the alpha waves exist, and there are many people who work on the theory that when you have magnetic reconnection, the particles that are accelerated have a speed of about, at the point of reconnection, they have a speed of about maybe 100 to 150 kilometers per second. For the same coronal loop, if I do alpha wave turbulence modeling, I expect a speed of maybe 30 to 40 kilometers per second. So there are observations that we both use and non-thermal velocity measurements. And I find those velocities to be consistent with alpha wave turbulence model, but people who work on magnetic reconnection, and there are many of my colleagues who done great work on magnetic reconnections, they get larger speed at the point of reconnection, but so far we haven't had an observation that would, even for the alpha wave turbulence model, you need very high resolution observation to be able to validate the theory. And there is an instrument that is being proposed to be built by NASA in the next few years. That is going to be one of the instruments that hopefully we can rely on for the non-thermal velocity measurements, and also maybe with the ground-based telescope observations, that would be a way of doing it. For the magnetic reconnection, I think you also need very high resolution imager, as well as an instrument that can measure the velocities to be able to resolve a few kilometers on the top of a coronal loop where the reconnection takes place. So hopefully with good observations, we would be able to validate both theories.
Thank you.
Sure.
So there's another question from El.
So he's asking, how is the density of the corona estimated?
That's a very good question. The density of the corona, I think, based on the, let me think about it a little bit. I think the density of the sun as a whole, based on there is the volume of the sun, measurements of the radius, and think about it a little. Density. That's a very good question. I can't think of the answer right now. Are they asking about how the density difference between corona and photosphere is measured, or how the density as a general?
I think just
Yeah,
in
well,
general, how
in general, I'm here.
Sure.
In general, I'm very much interested in the fact that the heat goes up as the density goes down, because
Yes.
it's a weirdness of plasma physics, because that's not the universal gas law. But anyway, so I was very much interested in how you get that basic idea, because that graph you showed at the beginning is very puzzling.
How the density is measured, I can't think of, I should know. I don't know how the difference between the densities measured. Let me just quickly look at, maybe I should have in one of my papers, I'm sure I mentioned this. So, but getting back, before I move to the paper and look for the answer, it is very puzzling, because if you're talking about high temperature, you're talking about the corona that has very high temperature and very low density. So it's not intuitive. You expect, if you are talking about high temperatures, usually there are more dense, and that's one of the interesting things about the sun. But let me see if I can find how this variation between the density is measured. And if not, then maybe I can.
Yeah, well, before we do that, Joe Henry seems to have a question.
I think he just left his hand up.
Sorry, did anybody else have questions?
I think someone just had a hand stuck on.
Okay, sure.
Well, that's a good enough answer for now. You don't have to bother with it right this second, but it's very intriguing to me just how unuseful classical physics is. Intriguing to me.
Sorry, I almost lost you. Sorry, what was?
Yeah, there's some kind of echo.
Sorry, I almost lost you. Sorry.
Yeah, there's some kind of echo. I will text it.
Okay, sure. I think maybe if I also had. Okay, sure. I think maybe if I also had.
Looks like we're running into technical difficulties here.
Yes, so I was. Sorry, can you hear me?
I hear you.
Yes.
Yes, sure. And I don't see maybe what I can do is I can send the answer to the gentleman who asked the question about the density, how the density is measured. Because I don't see him now.
Yeah, I don't know exactly how the sound is working, but I did post it to the post my comment to the chat.
Okay, sure.
Which is how it's very intriguing how poorly classical thermodynamics applies to plasma. It's really quite an amazing graph you get there at the beginning.
Sure. Sure.
If there are no more questions, I might just officially close the meeting and we can all hang around and keep talking.
Sure.
Let's see.
Thank you once again for very good talk.
Fantastic.
Thank you. Sure. Thanks. Thank you for your attention.
No, thank you very much.
Sure.
Zoom round of applause. It was very cool.
Thank you.
Very much.
There's a lot of people who image the sun in this club, and some fascinating images come out. There's a lot of people who may have just
It's very nice.
Okay. Oh, sorry, I was in a different tab. Okay, so with that, I think I'll officially end this meeting.
Sure.
And our next meeting will be Thursday, November 11th, 2001, or yeah, 2021 at 8 p.m. The next board meeting will be January 6th, 2020 at 8 p.m. So see you all then.